We've been talking about graphing polynomials, and here is a little bit more in depth about sketching the graphs of various polynomial functions. Whenever we want to sketch a graph of a polynomial function, so far we've only looked at them in factored form, and currently you don't have the knowledge to take something from standard form to factored form, so we're going to focus just on factored form for right now. You're going to need to identify the following things: the x-intercepts, the multiplicity, the end behavior, and the number of turning points. So let's go through and talk about how we can find each of these from our given polynomial function, and then we'll do a couple of examples. So first, the x-intercepts. The x-intercepts, or the zeros of a polynomial, are the values of x for which our function is equal to 0. And the zero product property tells us that if we have various things being multiplied together and they're all equal to 0, then at least one of them has to be equal to 0. So if f of x is 0, that would tell us that either this factor, or this factor is 0. So essentially, we want to set each of these equal to 0, and it'll tell us what our x-intercepts are. We would say 2x plus 3 is equal to 0, x minus 2 is equal to 0, and x minus 5 is equal to 0. We don't have to worry about the exponents because we would just undo those things. So for example, with x minus 5 squared, if we took the square root of both sides, we would be left with x minus 5 is equal to the square root of 0. But the square root of 0 is 0. Same thing here. We would have the square root or the cube root of 0, and the cube root of 0 is 0. So solve each of these. We subtract 3 from both sides. 2x is equal to negative 3. Then divide by 2. So one of our x-intercepts will be located at negative 3 halves, or 1.5. We have one at positive 2, and we have one at positive 5. Therefore, our x-intercepts are going to be negative 3 halves 0, 2 0, and 5 0. We always want to write them as either ordered pairs, or we want to say x-intercepts, or the x-intercepts are, and list them. Whenever you write something like x is equal to negative 3 halves, when we're talking about a graph, that truly would be a line on our graph. And so to avoid confusion, you always want to use this notation, or state the word x-intercepts and then list them after it. The next thing that we have to think about is the multiplicity. So the multiplicity is the number of times a given factor appears in the factored form of a polynomial. The graph of a polynomial will touch the x-axis, or bounce off of it, at zeros that have even multiplicities. The graph of a polynomial function is going to cross the x-axis at zeros that have odd multiplicities. And the sum of the multiplicities is the degree of our polynomial function. Finally, regardless of whether the multiplicity of a zero is even or odd, graphs tend to flatten out at zeros with multiplicity that are greater than 1. So things to remember is that we have a bounce, or it just touches the x-axis when we have even multiplicities, and crosses the x-axis when we have odd multiplicities. So example number 2 here, describe and sketch what happens at each of the x-intercepts of the following polynomial. So I'm just going to kind of focus on each little piece. So at this x-intercept was -3/2, the graph crosses the x-axis. And then here with the third at +2, the graph crosses the x-axis, but gets flat. And then at 5, the graph bounces on the x-axis. So we were kind of to think a little bit about what's going on here on this graph. Let's see. 1, 2, 3, 4, 5. And we haven't really talked a whole lot about what is going on as far as whether we're going to be above the x-axis or below the x-axis for each of these things. So we will talk about that a little bit more as we get into end behavior. But for right now, let's just kind of sketch out what's going to happen. So at -1.5, so here we would have a x-intercept or a root, and it's going to just cross through the x-axis. So it's either going to go from below the x-axis to above the x-axis, or from above the x-axis to below the x-axis. I know, just because I know what the final graph is going to look like, I know it'll go from above to below. So it's going to happen to go this way, and you'll see why in our future example. And then at +2, it's going to cross through, but it's going to get kind of flat as it goes through since we have a multiplicity of 3. So our graph is going to kind of come up here. It's going to get flat, and then go up. And at 5, we're going to bounce. So our graph will come down, touch, and turn around and go back off in that direction. Now for end behavior. The end behavior of a function describes what happens to the y values when the x values get very small or very big. And the end behavior is going to help us to figure out whether things are increasing or decreasing as they cross through the x-axis. The ends of the graph of a polynomial function will go in opposite directions if the degree of the function is odd. So they will go in opposite directions if our degree is odd. And the ends of the graph of a polynomial function will go in the same direction if the degree of the function is even. So think about it in terms of a linear function versus a parabola. A linear function has a degree of 1. That is an odd degree, and the ends of it go in opposite directions. Whereas a parabola is a quadratic function. It has a degree of 2. It's even, and the ends go in the same direction. And then our orientation is going to be based on the sign of the leading coefficient. So if our leading coefficient is positive and our degree is odd, being odd, it's going to have the ends go in opposite directions. Being positive, it's going to have to increase from left to right. Or in other words, as x goes to positive infinity, our f of x is going to go to positive infinity also. So we could have something such as a shape that looks like this, or you could have just a straight line. We could have many turns happening, but always as we move to the right or as our x values get bigger, we're going up in a positive direction to positive infinity. And also, as x goes towards negative infinity, our f of x values or our output values are going to go to negative infinity. So as we go this direction, notice that all of these are going down. If our leading coefficient is negative and our degree is odd, we will go in the opposite direction. It'll reflect. So instead of going as x goes to negative infinity, instead of our output values or our f of x values going to negative infinity, it'll now go to positive infinity. And as x goes to positive infinity, our f of x values are going to go to negative infinity. So we'll have graphs that look something like this, or you could have a straight line, or we could have multiple turns happening here. Now, if our degree is even, the ends of our function are going to go in the same direction. And if our leading coefficient is positive, think about a positive parabola. A positive parabola opens upwards, both ends go in the same direction. And we could have W shapes, or we could have even more turns in there. But overall, as x values go to negative infinity, our output values or our f of x values are going to go to positive infinity. And as our x values go to positive infinity, our f of x values or output values will also go to positive infinity. So both ends, as we go out in the negative x direction and out in the positive x direction, both sides go upwards. And we'll contrast that with a negative leading coefficient. When we have a negative leading coefficient, we're going to have more of like an M shape potentially, or possibly multiple turns in our shape. But both ends will be facing downwards. So as x goes towards negative infinity, our output or our f of x value goes to negative infinity. And as x goes towards positive infinity, our f of x values go towards positive infinity. So now example number 3 asks us to describe the end behavior for these following polynomials. Really, all we need to know is what is the degree and what is the leading coefficient. So here, our degree, you add up your multiplicities to get your degree. So So remember there's imaginary 1 here. So 1 plus 3 plus 2 gives us 6. So our degree is 6, and that is even. And our leading coefficient would be the 2x times the x times the x. So our leading coefficient is positive 2. And therefore it is positive. So the end behavior, well, it's even and positive. So both ends will go to positive infinity. Or you can even write down as x goes to negative infinity, f of x will go to positive infinity. You could say both ends go up. Part B here, our degree. This example, we're in standard form, so the degree is the highest exponent. Our degree is 3, so it is odd. And our leading coefficient here is negative. Since this is an odd degree, our ends will go in opposite directions. And since it's negative, we are going to be going down on the right-hand side. So the ends go in opposite directions. And it goes up on the left and down on the right. So we know we'll be going up on this side and then down on that side, and something's going to happen in between there. Not really sure exactly what will happen in between, but we know that we're up in this direction and down in that direction. For C, our degree is 4. It is even. And our leading coefficient is negative 0.5. So therefore it is negative. Since it is negative and even, both ends will go down to negative infinity. Or we know that both ends will be going down, but we don't know what's going to happen in between there. Here, both ends were going up. And then the last one, our multiplicities 2, 2, and 1. So our degree is 5, and this leading coefficient is positive 1. So it is positive and odd. Therefore, the ends are going to go in opposite directions, but it'll go up on the right. So up on the right and down on the left, and something's going to happen in between there. The last thing with graphing is the number of turning points. A turning point of a graph of a polynomial function is the point where a function changes from increasing to decreasing or from decreasing to increasing. And a polynomial of degree n will have at most n minus 1 turning points. It could have less, but it can never have more than n minus 1 turning points. And we'll go into this a little bit more later. It has to do with multiplicity, and it also has to do with the number of real roots versus the number of non-real roots or complex roots. And so right now we're not going to bother a whole lot with that. So let's get into some examples where we're sketching some polynomial functions. Example number 4 has us sketch this polynomial. F of x is equal to 2x minus 3, x minus 2 cubed times x minus 5 squared. So first off, we need to look at and identify what are the roots of this polynomial. So what are the real roots? Well, the real roots come from our factors here. So our real roots are going to be at negative 3/2, at positive 2, and at positive 5. This was the function that we used in a couple of other examples. And it's whenever each linear factor is equal to 0. Other things that we know that this is a degree of, 2 plus 3 plus 1 is 6. So it is even. So the ends go in the same direction. They're either going to both go up or they're going to both go down. And since it is positive, the ends are both going to go up. So positive leading coefficient. So we know that both of our graph ends are going to be going up. Then we can see what's happening at each root. At negative 1.5 or negative 3/2, it crosses through. So it's going to go straight through at 1/2, negative 1.5, excuse me. And then at positive 2, it's going to go straight through, but it's going to kind of flatten as it does that. So we're going to have to turn around somewhere, and you could figure out what the y-intercept is, but we're not going to do that right now. So this graph is going to go down, and then it's going to turn around at some point. It's going to come up here, and it's going to get flat as it goes through 2. And then at some point, it's going to have to turn around and go to 5 and bounce at 5. So it touches and turns around and then goes back up. So there's the general shape of our function. Our other example here, part B, our real roots are going to be at negative 6, at negative 3, at positive 3, and at positive 6. Our degree is 9. And it is negative oriented. Since it is an odd degree, the ends go in opposite directions. And we have a negative leading coefficient. So therefore, we know that it's going to be going up on the left-hand side and down on the right-hand side. So our graph is going up on the left and down on the right since it's negative. Okay, so we're going to pass straight through at -6. It's up on the left, so we're going to pass straight through at -6. And then we turn around at some point, and at -3, we're going to bounce. But it's going to get relatively flat as it hits the x-axis. So it gets somewhat flat here. Turns around again. And then at +3, we're going to go and flatten as we go through. So it's going to get flat as it goes through at 3. And then it'll turn around and cross through at +6. And we can check and see our ends are in fact going in opposite directions. We have a bounce or a turnaround at -3, and that's because we have an even multiplicity. We have a passing through at +3, but it gets kind of flat because of this higher odd multiplicity. And our last example, example number 5, use this given information to write a possible equation for the polynomial function. So some things, part A, it's giving us a graph. Because the ends are going in the same direction, we know that this will have an even degree. And we know that it has a negative leading coefficient. Since both ends are going down. We have 3 real roots. We have real roots at -5, at -3, and at +5. And the root at +5 has a multiplicity of 2, or an even multiplicity. Based on the fact that it doesn't look very flat here, I would say it has a multiplicity of 2. But because we don't have a ton of information about this graph, if you gave a 4 multiplicity on this turnaround, it would be acceptable. So I'm going to write each of my roots as linear factors. So -5 will be x plus 5. -3 will be x plus 3. And +5 will be x minus 5. Since it's negative, I'm going to need a negative out in front. And this 5 root needs a multiplicity. I'm going to give it a multiplicity of 2, but as I said before, you could potentially have a multiplicity of 4 or 6, but 2 is probably the best answer. And then our last problem, a polynomial function with a degree of 5 and having a triple root at x equals 1, so that's a root with a multiplicity of 3, a double root at negative 3, and as x goes to negative infinity, f of x goes to positive infinity. So as we're moving to the left on our graph, we're going up. So it's going up in this direction. And it says it has a degree of 5. So this is an odd degree. And since it has an odd degree, the ends go in opposite directions. So it's going to do something, and then it's going to go down on the right. Since it's going down on the right, or overall in this downwards direction, that tells us that it has a negative leading coefficient. And you can even reference back to our chart that we did over here. We have this kind of shape or this kind of shape, something like this. It has a leading coefficient that's negative and an odd degree. And then we have roots at 1 and negative 3. We're going to have y is equal to negative x minus 1 cubed, since it was a triple root, times x plus 3 squared, since it said it was a double root.